Welcome back, everybody, after lunch. It's so nice to be back, and thanks to everybody who's organizing this. Really, really awesome. Yeah, my talk is about SwiftUI, and it's a deep dive into the layout system of SwiftUI, actually. So we're not going to talk about all of SwiftUI, but just about the layout system. And layout in SwiftUI is actually, if you look at the slides that people always put out, it's really easy, right? It's just simple, and it actually, under the hood, it is pretty simple, yet anybody who has used SwiftUI in practice knows that in practice it's actually quite hard. And so I think having a better understanding of what's going on there really helps, and that's what we're going to have a look at. Okay. So let me go to the next slide, and this is a slide saying we're going to switch to Xcode, so we'll be doing a bunch of live coding and going back and forth. Okay, so here we have some text. I'll make it a little bit larger so you can see it well. And this works. One of the things to notice is that in SwiftUI almost everything is centered by default. That's really cool. It's a default that you have with almost every view, almost everything. And it makes things look good by default. And that's one of the key things that SwiftUI wants to do. And so we could do like a background on the text. And that works. And we can see that the background is exactly as large as the text. And that sort of happens automatically. And we can also make the background slightly larger than the text. So we could do dot padding. And now the background is around the padded text. And this is already where things start to get confusing if you're not used to this. Because what happens if I swap these two modifiers? So I do the background first and then the padding. All of a sudden we get a different result. And so why is this? Well, the first thing to notice is that SwiftUI is not like UIKit. So it's not setting properties here. It's wrapping views. And so let's go back. I'll remove the font. You noted what text is on the screen now. And the key thing here is that if we look at the view tree, we can actually see the difference a little bit. So we could see here that in the view tree, we have a background as the root node. And that background has a padded text as the primary child. The secondary child of that background is a color. It could be anything, right? Like, so we could say dot gradient, and then we have a gradient as a secondary child, and you can put any view you want in there. Now, what happens if we swap the order of these modifiers? Now we get a very different view tree. And I think understanding how your code translates into these trees is essential to understanding SwiftUI and to be effective with it. So you need this for the layout system. You need this for the state system, for the environment, for animations even. And like understanding what happens at the view tree level is something to always keep in mind. Okay, so it's maybe a little bit confusing. Let me go back to the large title. But like you can start swapping the order of modifiers, and maybe like then you can make your SwiftUI layout work for you. But we're going to make it a little bit more confusing. So I'll wrap the text in an H stack, and now we're going to add like a colored green and a colored blue. And let's do a frame so it looks a little bit nicer. And this looks okay, but it's also weird if you think about it, because why is the text laid out over 2 lines? That doesn't make sense, right? There's enough space. If this was auto layout, it would easily fit. And so what's going on here? So we're building up all kinds of questions. Now, if you are good at Stack Overflow, you can search for things like, oh, text doesn't work. And somewhere in the Google results, you'll find like somebody recommending you should use fixed size. That's going to solve all of your problems. So we can try it. So we'll have fixed size here. Well, this is definitely not the right spot, but let's try moving it on the text. And our problem is solved. And like now we can be happy, right? But it's not actually correct. And it works for this example, but what happens if we have longer text? Now, the text will basically grow as large as it needs to be. So this is clearly not right. we want at least the text to be broken into 2 lines and then truncated. Like now the size, like the text is basically rendering itself at a fixed size. Disregarding any kind of device bezels or whatever, right? So that's not correct. So what should we do instead? Well, we should be using layout priority. And we'll give it a layout priority of 1, the default is 0, and by giving this higher layout priority, the HTAG sort of makes it work. And so we're building up these questions. Why did the text render into 2 lines? Why did fixed size seem to solve it, but is it not really? What is this layout priority doing? Okay, so that's a simple view. Now, I'll make it a little bit more confusing still, and then we're going to hopefully answer the questions. So I'll remove the layout priority again. I'll remove the frame here, and we're going to change it to a V-stack. So we could see that this V-stack nicely fills up the safe area. But we might have long text, so why not wrap everything inside a scroll view? And what's happening now? Like, what's going on here? All of a sudden, like the rectangles, they become super tiny. Like, how can that possibly be? And so that's what I sort of mean. Like, it sort of looks very clean on the slide and everything seems to work, but then you have this very strange behavior and what is going on? So that's what we're going to look at. Okay. Here we have the same view tree as before, where we have the padded text. And the way SwiftUI works is that it proposes a size to your view tree. And so in SwiftUI, every parent view proposes a size to its children. And then the children choose their own size based on that proposal. That's all of the layout system. Everything works like that. And so here we are proposing 300 by 200 to the root view. And the root view was the background view. Now, the background view says, well, if you propose me 300 by 200, I'm going to propose that same value to my primary child, which is the padded text. So we're proposing 300 by 200. And the padding is kind of special. So the default padding for this platform is 16 points. We just wrote dot padding, right? And it added the platform default padding. So that's 16 points. So that's 16 on the leading edge, 16 on the trailing edge, 16 at the top, and 16 at the bottom. So that's basically, put in a different way, that's 32 points horizontally and 32 points vertically. And that's what gets subtracted here. So if we go one step further, we could see that instead of 300 by 200, we're now proposing 268 by 168 to the text. And so the text then says, well, I don't need that much space to render myself. Like, I can render myself fine at 169 by 25, and that's going to be my size. And so that's the result. And I make it look maybe a little bit fancy with proposing and reporting, but you can really think of this as a function call, a method call. So we're calling a function on text, like, what is your size for this given size? Right? Okay, so the text says I'm like 169 by 25, and now the padding is going to add back to that. So it's going to say, well, if you're 169 by 25, I am going to report 201 by 57. And so now we're done with the layout. So the background says, okay, that's my size. And then actually there's one more step, because when we are finally rendering our view on screen, the background modifier is going to take that size of our padded text, and it's going to propose it to the caller. And so now the caller says, I will take whatever you want. Like, if you give me 201 by 57, that's going to be my size. And this is in general with all shapes and things like that. They will accept any size we give them. And so color is a view in SwiftUI, and so it will accept that. And we can really think of every view in SwiftUI as having some method like this, size that fits, and it takes a proposed size, which is a CG size, and it also returns a CG size. And so every view has its own implementations for this. I'll just write fatal error so that this compiles, and so that we can keep it on the screen. It's not the entire truth, but it's very close. And so think of every view as having this implementation. And that's basically the arrow we saw before, right? We're proposing a size, and the view reports a size. And the reporting is the result. Okay. Now to the H tag. So here we can see an H tag, right? And it renders on 2 lines. And if we actually do make it wide enough, it will at some point render onto a single line, but not here. And we can actually have a look at how the H tag works internally to understand this behavior. So here we have the internal state of an H tag. On the left, we have the remaining subviews. We have 3 remaining subviews. On the right, we have the remaining width, 280 points. And the idea behind the HTAG's algorithm is that it tries to distribute its horizontal space as equally as possible among its subviews. And then it kind of makes sense. So remember how basically the color and the text and the other color were all like kind of the same width. And so that's what the HTAG is going for by default. And so we have 3 views remaining. The first thing that's happening is that the HTAG computes the flexibilities. And this is very strange, but it will make sense, I think. So what's the flexibility? Well, a view, for example, the blue color, if we propose it a very large width, it will accept it. If we propose it a 0 width, it will be a 0 width. And so we can think of the difference as the flexibility. And so this blue rectangle is infinitely flexible. The text, if we propose it a very large width, it will only become as wide as it really needs to be. And if we propose it a very small width, it will become very small. And so the difference between those values is much less for the text. So the text only has a flexibility of 77 in this case. And then the HTAG orders by flexibility. So it says, I'm going to start with my least flexible view. Okay. So once it's ordered, it can ignore the flexibilities, and now it needs to first subtract the spacing. We did not specify any spacing, so we get the default 16 points. And so we had 280, and now it subtracts 2 times 16 points because we have 3 views, 2 spacers in between. And so it has 248 remaining. And here's sort of where hopefully it starts making sense. The HTAG is actually going to propose a third of its remaining width to the first view, right? So it has 248, so it's going to divide that by 3 because there are 3 remaining views, and it's going to propose a third to the text. And so the text says, well, if you propose me 83 for the width, I'm actually going to render myself onto 2 lines, so my size will be 44 by 34. And so now the HTAG has 204 remaining, and it has 2 remaining subviews. So it's going to take half of that and propose it to the first remaining subview, the blue one. And that will gladly accept. And then it's going to take the other half and propose that to the final remaining subview. And then it's done with the layout horizontally. And that whole flexibility thing, that was a little weird, right? But if you think of it, it does make sense somehow. Because what would happen if it wouldn't do that? So let's say the HTAG starts proposing by like a third to the blue rectangle. Well, the blue rectangle will accept it. Then it proposes a third to the text, which doesn't need the full width of that 1/3. And so it will become narrower. And then it would propose whatever is remaining to the green rectangle, which would then become quite wide. And so it would be much wider than the blue rectangle. And so in that sense, it kind of sort of makes sense why they're doing it like that. Okay. Here we have our view with fixed size, and that looked like it was working, right? Like we can see if we make it smaller, we can see it be stretched beyond the bounds a little bit. And why was this working, or why did it seem to be working, and what's going on there? And the thing that fixed size will do is it will basically, essentially, it will ignore the proposal, right? So the text will get proposed maybe a third of the available width. It will completely ignore it and just become its ideal size. If you're used to auto layout, that's kind of like its intrinsic content size. So we can go over the steps here as well. We have, again, this internal HTAG state. We have the 3 views. We have the same remaining width. And the HTAG is going to first figure out the flexibilities. And here we can see something interesting, right? The flexibility of the text is 0 because it will always become the same size no matter what we propose. So it will take the difference between a very large proposal and a very small proposal, which is 0, the difference, because it's always the same size. And so the text is still our least flexible view. The h-tag is going to discard the flexibilities. It's going to subtract the spacing. And then it's going to lay out those views. And in this case, it's going to propose 83 to the text. And as I mentioned, because of the fixed size, the proposal is completely discarded and not regarded. And so the text says, well, I'm going to be 90 by 16. And then the h-tag has 158 remaining, and it's going to distribute it equally among the 2 remaining views. So first, the blue rectangle gets half of it, and then we only have 1 view remaining and 79 points remaining, and so that's what the green rectangle becomes. And now what does the layout priority do? That's the last one, right? So here we set the layout priority of 1. And as I mentioned, by default, every view has a layout priority of 0. So when there's no explicit layout priority set, the h-tag will actually ignore it. But in this case, we have a layout priority of 1, and so the h-tag will look into it. So let's again go over the steps. So we have our 3 views and the 280 points. And there's actually a step that I lied about, and it's actually happening before the flexibilities are computed, and that's the computing of the layout priority. And so we explicitly specified this. So our text has a layout priority of 1, and the other ones are 0. And now we first order by layout priority, and then the next step, and this is kind of special, is that the h-tag groups the views. And so we have one group with a higher priority and then one group with a lower priority. You can have as many groups as you want, but in this case, we have the 2 groups. We have 280 points remaining, and we're going to subtract the spacing first. And now something weird happens. The h-tag is actually going to take all of the remaining width and propose it to our highest priority group. And because there's one view, it receives the entire remainder. And so that text says, well, you know, I don't need like all of that. Like I only need like 90 points to render myself. And so then the h-tag actually still has some remaining space, and it's going to propose that to the 2 remaining subviews. So that's basically as before, because now we only have one group left and just 2 flexible subviews, so that the space gets distributed equally. And so something to keep in mind here is when you're using layout priority, you have to be quite aware of the flexibility of your views. If you put like another rectangle and give it high layout priority, the h-tag will actually propose the entire remainder, and there will be nothing left for the other views. In reality, you can also set a minimum width on your other subviews with a lower priority, and the h-tag will take that into account, but it's just something to be aware of. And like we can see, like here, because of the way the whole proposing and reporting works, there's enough space left for the other 2 views. So I think we solved a few of the weird questions we came up with, right? Like, so we know now exactly how the space in an h-tag is distributed. There's one more thing when it comes to h-tag layout, and that's the alignment. And so by default, as we saw, everything is centered, and that's the case here as well. We can change this, so we can have top alignment, we can have first text baseline. Oh, something is strange here. We can have bottom alignment, and let's look at how that works. So we again have 3 remaining subviews, and all of these views have all of the alignment guides. So the yellow rectangle has a top, a center, and a bottom. The text has a top, a center, and a bottom. And the orange rectangle does so as well. All of them also have a first text baseline. And so every parent can always ask its children for whatever alignment guide it needs and use that to align all the views. So let's start with the yellow rectangle. We had bottom alignment, and so it asks for the bottom. And that question gets asked to the yellow rectangle, and it responds in terms of its own local coordinate system. So this yellow rectangle is 80 points tall, and so the bottom would be 80. The yellow rectangle has no idea about the parent or about its siblings. It just says, well, I'm 80, so that's my bottom. Then the age tag is going to ask the text for its bottom. The text has a height of 64. And so it responds 64. Again, it has no idea about the parent. It has no idea about the other two rectangles. It just says, well, my bottom is 64. And then finally, it's going to ask the orange rectangle, and that says, I'm 80 as well. And so now we have basically all the three views with their alignment values, and the age tag can put them on a single line. So it really makes sure that all these red lines are on a straight horizontal line. And that's the essence of it. So let's look at what happens when we, for example, switch to first text baseline. We get a very different behavior. This even gets taller than the stack. And maybe let's try the top one again, just to get an idea of how that would work, or actually center. So when we do center, the age tag is going to ask a different question, right? So all the alignment guides are all still there, but now they respond with this center. So in this case, it's going to be 40 because the rectangle is 80 tall. And with the text, it was 64, so it's going to respond with 32, right? And so again, with the orange rectangle, and now the age tag can align all of them. So that's what we see here. And then finally, the first text baseline, that's where it gets interesting. So if we run this, we could see, again, all the alignment guides are there, and we're going to ask for the first text baseline of the orange, of the yellow rectangle. And that yellow rectangle it doesn't have any text in it, and so by default, the first text baseline is the bottom, so it responds with 80. The text, of course, has a baseline, so that's basically where the letters are kind of sitting on. You know, like the H sits on the baseline, the comma extends beyond the baseline. And so the text responds with its value for that, which is 23.3. And then the orange rectangle responds. And then SwiftUI can actually lay out those views. So we have all the baselines, and so it's going to make sure to position the views that all of these alignment guides are in a single horizontal line. So I think now we should know enough to do something more complicated. Okay. We're going to be writing a simple transaction view. So imagine we're working for a credit card company and we want to display a transaction for a credit card. So I'll delete all of this. And we'll just do a transaction view here. So let's create a new struct. And I mean, how hard can it be, right? And so I live in Germany, and we have these really long company names there, like Deutsche Bahn, Fernverkehr. That's pretty wide already. And then the designer wants us to do the price in a kind of special way. So let me just create an H tag here. So they want like 0, 0, and then they want to have different styling for the part after the decimal separator and the part before. So let's actually say 99 euros. And so this needs to be a large title, and this needs to be a title font. It's not quite right, obviously. We have spacing between the 99 and the dot, so let's get rid of that first. So I'm going to create an inner H tag, and then we can set the spacing to 0. So that looks a lot better already, but the alignment is all weird, right? And we know now that we have first text baseline alignment, so let's use it. So I'll add an alignment and say first text baseline. And this looks a lot better already. And we'll also use that same alignment for the outer H tag. Okay, so that's great. And I think this looks quite nice. We'll maybe do a foreground style secondary. The semantic one also responds to light mode and dark mode. And then, of course, we need an icon because we need icons. So we'll use an SF symbol. And let's search for something train related. This one is nice. And one of the cool things, I don't know how easy it is to see that, is that these icons, these SF symbols, they all have adjusted baselines, so they will actually look nice. We can show this. So let's do a spacer over here, and now we can actually zoom in. And if you want to debug, for example, how things are aligned, there's this trick where you can use an overlay. So let's try that. We can do an overlay, and we can do a colored red, give it a height of 1, so we have a horizontal line. And by default, this will get centered, but we can say alignment first text baseline, and now we can exactly see the baseline. And so you could see here, I think I can zoom in further, that the image extends just a little bit beyond the baseline. So that's the SF Symbols designers that did this for us. OK, so we're almost done. Not quite. Let's have a look at dynamic type. So I'll enable dynamic type here. This, not the orientation, dynamic type. This is not quite nice, like with the 2 lines, so let's fix that first. We'll set a line limit of 1. So that's a little bit better. Let's increase the dynamic type size further. That's not good, right? Like all of a sudden our price broke. But we know what to do now, because we want to give our price a layout priority. And that's going to solve this for us, because it gets offered the remaining space. So let's give this a layout priority of 1, and then try dynamic type again. And so that's much better. I mean, it's not readable, the name of the company, but this is, at least the designers will be happy. OK. What is also cool, I don't know if it's, let's make this image a little bit larger. So the SF symbols, they will respond to font sizes. They're meant to be used together with text. And so this will also work with dynamic type. So we can see as we increase the type size, the image also increases. That's quite nice. OK, so we're almost done. But now, of course, the designers will come back again. And they will say, like, well, we cannot use the SF symbols and copyright, and we need to use our own icons. OK, let's try that. I have a train image ready for us. And this is the default behavior of an image when it comes to sizing. An image will basically ignore whatever is proposed, and it will become its underlying bitmap size. So if you have a 1,000 by 1,000 image in your asset catalog, it doesn't matter what you're going to propose. The image is going to be 1,000 by 1,000. But we can change it. And there's only one change we can make. We can make it resizable. And then the image will accept anything. So we could say resizable, and now it will become exactly what we propose. So I don't know. Does anybody have a solution? No, we'll fix it. OK, so this is, I mean, horizontally, if we think of it like that, it's kind of nice. It's not the worst, but vertically, of course, we don't want that stretching. And so we can use a special modifier for this aspect ratio. And it's kind of magical in that it figures out the underlying aspect ratio of the image. And so we're getting a lot closer. It's still way too large. And so we can force this, for example, to have a height of 28, which is, I think, matches the dynamic type size. OK, so that's much better. The magic number is not quite good. This is not like the magic that Pavel showed us, but this is, I think, the bad kind of magic. Let's add our overlay, because I think the alignment is not quite correct. So let's zoom in a little bit. Yeah, and I mean, it would be nice if the cards would hang on the baseline, right? That would be amazing. And so we learned how an HTAG aligns its subviews. It will ask the questions to all of its children. And so in this case, our outer HTAG on line 19 is configured with a first text baseline alignment. And so it will ask each of its subviews, what's your first text baseline? And so an image view, by default, this is not an SF symbol, but a regular image view, it will just respond with the bottom value. But we can overwrite for any subview the answer to that question. And so we do that with an alignment guide. And we can say, well, if you're going to ask me for the first text baseline, it's called alignment guide. If you're going to ask me for the first text baseline, I want to have a different response. So I could say my response is 0. which is the top of myself. So the top of the train icon is aligned with the baseline of all the other views. Or you could say dim.height, which is, the dim is kind of like a CG size, and it has a width and a height. And so then it responds with the bottom. And we can also tweak this. So we could say like -2. It's not quite there yet. Let's try -3. OK, so now we're good. So we're done. Now, this is the default dynamic type setting. And of course, we hard-coded all these values. So this is always going to be 28. And so that's not nice. So we lost again. But this is, I think this is really cool what we can do now. So we can add a scaled metric. And we could say we want to have a scaled metric that's relative to the large title font. So it scales up as the large title font scales up. And we could say train height equals 28. And I'm going to duplicate that and say baseline offset. And it's going to be 3. Oh. So 3. And now we can use those two values over here. So we could say train height, and we can say baseline offset. So now let's see what dynamic type does. Yeah, this is much better. So we're scaling up with dynamic type and respecting all of that. It did become like the code became quite complex. It started out simple enough, but yeah, it's definitely a lot. So we can disable our overlay here. I don't think we need it anymore. OK. We're almost done. So I told you I was lying. This proposed size, and now we get back into the theory part again. This proposed size is not actually a CG size. So it's called proposed view size. And just like a CG size, it has a width and a height. But the difference is either one can be optional. And so a nil proposal means become your ideal width, if you propose a nil width. A nil height proposal becomes become your ideal height. And that's actually what the scroll view does. Like it has all this infinite space available vertically. And so the views can become their ideal height. And this is also what's used by the aspect ratio modifier. So we can have a look into that. Here's a simplified version of our aspect ratio modifier that we just used earlier, which was kind of magic. It sort of did what it should do. So what happens here? We're proposing 200 by 200 to the aspect ratio modifier. The aspect ratio modifier then needs to figure out the underlying aspect ratio of the image. Right? And it works actually with any view, not just with images. And so how can it figure out the underlying aspect ratio? Well, it's going to propose, oh, wrong button. It's going to propose nil by nil, which means it's asking the image view for what's your ideal size. And the image says, well, I'm 154 by 91. Right? And so the aspect ratio will then take that and take the original proposal, 200 by 200, and it will fit a rectangle inside there. That's the correct aspect ratio. So a modifier or a parent view, it can propose more than once. And so that's how that works. And if we would change it to fill, we can see that we have very different proposals. So then we had 200 by 200. It's again going to ask nil by nil to figure out the underlying aspect ratio. The image still has the same response, but then the aspect ratio fits a rectangle inside that 200 by 200. So that's how the aspect ratio modifier works. And the scroll view, that was also kind of magical, but it's the same idea. So let me switch to the tree view. So what if we are proposing 200 by 200 to the scroll view? Well, it actually is only going to make one slight change. It's going to propose 200 by nil to its children. Or in this case, it's a single child, the v-stack. And the v-stack says, OK, well, I don't need to distribute any vertical space anymore, so I'm just going to propose nil to all my children as well for the height. So it's proposing 200 by nil to the text, It's proposing 200 by nil to the color. And this is why your views get so small, because the color is going to respond with 10 for that nil dimension. That's the default dimension that all the shapes in SwiftUI will respond with. You can change that with an ideal height, but this is why scroll views break your layout. Okay. Before we call it a day, a lot of these explanations are on a new website called the SwiftUIFieldGuide.com. You can check it out. It's all interactive and it has explanations. If your company is interested, we also teach workshops in-house, online, or in person. If you're interested in that at all, just let me know and find me after the talk. Thank you.
Thank you very much, Chris. Okay, shall we delve into some questions from the audience? Take it away. You use a great presenting solution. Could you please share some insights on that?
Yes. So the presentation is made with SwiftUI, and not just any SwiftUI, but it's SwiftUI in the browser. And so that's the website. I'll show it here. It's the field guide, and I ported the SwiftUI layout system to the browser so we can explain it. And so I'm using that also to do the presentation. I don't know. Yeah, you could see it right on the screen. So yeah, and so you can find the same examples over here as well. So this is like the HTAG example. So if it was too fast or too confusing, hopefully going through it again yourself can help.
Okay, moving on. Great way of showing the proposal algorithm of HStack. Is the algorithm documented anywhere by Apple?
It's not, I think. I mean, a little bit. So in the, I think it might have been 2019 WWDC talk by John Harper and Dave Abrahams. They actually talk about this and they talk about like flexibility and all of that, but sort of in a hand-wavy way. And when you notice what I just said, then kind of that talk, for me at least, made a lot more sense in hindsight. What you can do, and I'll show you the link for that, you can actually, if you don't believe anything I said, you can go here to the debugging page, and you can use this code. This is a custom layout in SwiftUI that you can wrap any view in, and it will show you exactly what was proposed and what was reported for any view. And so if you have a view, you apply this debug layout, you put that view in an HTAG, you will see how the HTAG first proposes first proposes 0 for the width, then it proposes an infinite width, and then finally it lays out the views in order. So if you don't believe me, just run this code and then you can figure out all of these things for yourself.
Okay, shall we do a couple more? With SwiftUI, the preview on larger projects always fails and stops loading. How was your experience?
Yeah, I feel always like a little bit of a fake. So I learned a lot about the SwiftUI layout system, and I think I know a lot about it, but I don't know about building real applications. I think all of you are much better at that than I am. So, you know, my applications, like if it's like a few hundred files at most, like that's very complex. And so, yeah, I don't really have an issue for that, a solution for that. I have some suggestions that friends made. So one thing is to split up your project into multiple modules or maybe packages. Another thing is to keep your previews very simple. So you can, like, let's say you're displaying a list of data that you load from the server. You could actually have 2 separate views. So one would actually be displaying, and the other view would be loading the data and calling the first view. And so then your previews could use the static view with static sample data. And maybe that will help a little bit. But yeah, I don't have any better solutions.
Okay, let's take another one. Thank you for an excellent presentation. Is your SwiftUI knowledge based mainly on your experimentation, or did you consult with Apple engineers?
I wish I could have consulted. I think I had to learn everything myself, and you can sort of put pieces together at some point. And the layout algorithm actually helped so that we could, for the first time, see this proposal and reporting. I think having to learn it myself without any help really helped me like gain a deeper understanding, but it wasn't very time effective. It took me a long time to understand all of it. I think, like the other part I did to understand all of it is, for example, like implementing it myself. And if you ever want to learn something at a very deep level, that's a technique that works really well for me. So the moment I know how to implement it, it's just in my head. I don't need to think about it anymore. And before that, you always need to think like, what does the padding do? What does the H tag actually do? And when you've written it down once and try to be very close to the reality, then I think you can learn a lot.
Let's take a couple more. What is the view mirror that you used at the beginning?
Yeah, that's a great question. So the view mirror is actually a view. It's an internal tool we have. So what it does, it takes the type of a view, so we can print it maybe. Let's. This is a little scary. I'm in the wrong keyboard layout. Okay. Let result equals, and let's print the type of this view. It will be horrible, I think. Let's return the result. Oh, now my computer stopped working. That's great. So the view mirror takes the type that the view has, and it parses that, and it turns it into a tree. And so it's basically taking the type of your SwiftUI view, because as we saw, like when you have, for example, a text, the type will be text. But if you add a padding, it will be something like modified content of a text of a padding layout. And if you add like an overlay to that, you will have a modified content of a text with a padding layout, and then the overlay thing. And so your type gets really, really complex. And so it's just parsing that and displaying it. Great question.
Okay, let's take something else. Depending on the views within the stack, the spacing can be 8 or 16. Is there a similar system where the view has a preferred spacing on top and bottom?
Yeah, there is something with that, with preferred spacing, and I never understood how it works. So I don't know exactly. You can, in the layout protocol, you can define preferred spacing, and that's how I know that there is something like that, but I never really understood how that works. So normally in a stack, you'll have spacing between the views, but then when you put spaces in it, sometimes things can change. And I think, and I don't know this, so please don't judge me on it, I think there are special cases when you put text in stacks, sometimes it can sort of adjust. I think this is mainly with a vertical stack. It can adjust the spacing so that the text looks more like multiple lines. But I'm not exactly sure. So yeah, the short answer is I don't know.
Okay, I'll take the last question. How long have you been sponsored by Deutsche Bahn?
No, I had to pay everything myself, and I came with both the Deutsche Bahn and the Czech Railways.
So both of them.
Yeah, in fact, I had a Deutsche Bahn. We have these Germany. Well, no, it's too long a story. I'll tell you a Deutsche Bahn story afterwards.
Thank you very much, Chris Eidhof.
Thank you.